All right, so we're going to talk about electromagnetic induction. There's a lot of applications based on this. Okay, so this is an important chapter. And what this chapter is about is the following: this one equation. Okay, and actually, there's a lot of your electricity is produced this way. Photovoltaic cells work differently, but based on this equation, all the dams, all the windmills, all the coal power plants, they're based on this equation. This and this one. Okay. So, what this equation is telling you is the following. See, time-varying magnetic fields produce electric fields. Okay. And I'll show you a configuration. So the form of the equation tells you the following. So for instance, if you have magnetic fields like that, I'm just showing you one configuration. Magnetic fields are denoted by B. And let's say if the magnetic field B is increasing, what this will do is, so this increasing magnetic field will produce an electric field all around it, like that. And the electric field will be in that direction, okay? And that's what this equation is telling you. And if the field is there, the further out you are, the weaker the electric field, okay? Now, well, what does the electric field do? Now, if you put a wire there, it will drive a current in the wire without any batteries. So this time-varying magnetic field produced an electric field. Yep.
Since the opposite direction is the right-hand trick?
Yeah. So what this you learn in Lenz's law, that the direction of, so if you put a wire, it'll produce a current in this direction. And what this current is trying to do is produce a magnetic field in this direction. So the induced current will produce a magnetic field opposing what is producing it. So this is the classic example of biting the hand that feeds you. Okay? All right, so that's what this chapter is about. Okay? All right, so here I'll show you a bunch of pictures. So here's a magnet. Okay. So again, how do you produce time-varying magnetic fields? You grab hold of a magnet and move it around. Okay. So here's a magnet. Okay. It produces magnetic fields all around it. Now, when the magnet is stationary, you see there's no induced current in this coil. You move this magnet back and forth, and you're inducing a current in this wire. See, there's no battery connected to this coil of wire, and you're inducing a current. Okay. What's happening here? This battery is driving a current in this coil, and you saw from the last chapter that produces a magnetic field in there. And if you move this, oscillate this back and forth, it's just like moving this magnet back and forth. And you're inducing a current here in this coil, okay? No batteries in this coil, and you're inducing a current. How about here? Okay, so when the switch was open, there's no current through this coil. When you close the switch, you induce a current, and the magnetic field inside that coil goes from 0 to its maximum value. And so for that fraction of time while the magnetic field is changing, you're inducing a current in this coil. All right, so let's okay. So, okay, actually, let me tell you the Faraday's law before I show you the most important application. All right, so here's another illustration. Again, time-varying magnetic fields are inducing electric fields. Okay, so if you have wire like this and you change the current in this wire. Okay, so again, the current is like that, and if you use your right hand, your fingers point in the direction of the current, and the thumb points in the direction of the magnetic field. So that's the magnetic field. So as this current is increasing, the strength of this magnetic field is increasing. And so the magnetic field through this region is changing, and that is inducing a current, an electric field. The electric field is in this direction, which induces a current like that, which is trying to oppose the field that produced it. All right, so this is the induced current. Okay, so what if I stop changing this current? What do you think will happen?
The magnet won't vary by time anymore?
The magnetic field doesn't change with time anymore. This induced field does not exist anymore. Will go to zero, and this current will stop. Okay, so you can induce a current in this wire as long as you're changing the current in this wire. Okay, so just hook this thing to a AC outlet. This current will change all the time, and you'll induce a current, an AC current here. A change in current in this circuit induced a current in a nearby circuit. And we'll talk about this in the next chapter, that is mutual inductance. And this is not just academic. You know, imagine a factory floor with a whole bunch of machines. You're done for the day, you're tired, you turn off this machine, and this machine that was off gets turned on. This thing happens. Okay? So of course you gotta magnetically isolate that. Okay? All right. So we'll talk about magnetic flux. Just like water flux or material flux, it's how much fluid is flowing and all that. We also talked about electric flux. So magnetic fluxes, you can think of them as how many field lines are threading, magnetic field lines are threading this area. Okay? And just like all the other fluxes, we'll define this as the magnetic field, the dot product of the magnetic field dotted with the area vector. Okay? And the flux is denoted by phi, the subscript B telling you that it's a magnetic flux. Okay? And in this configuration, when A and B are perpendicular to each other, the flux through this area is zero. Okay? All right, so here's what Mr. Faraday's law states. The EMF induced, remember, what does this guy say? This law, this is Maxwell-Boltzmann's equation, changing magnetic fields induce electric fields. Okay? And the line integral of the electric field is EMF between those 2 points, the voltage between those 2 points. Okay? So what this Faraday's law says is the EMF induced in a circuit is equal to negative of the time rate of change of magnetic flux. Okay. All right, so here's magnetic flux. Magnetic flux is B dot A, okay, which is B times area vector times cosine of the angle between them. Okay, so if you have an area like that and B field like this, theta is that angle. All right, so let's make sure we understand this equation. So the EMF, induced EMF, okay, is time rate of change of BA cosine theta. Okay, so you're inducing an EMF in your circuit as long as this right-hand side is not zero. Okay, now we're going to generalize this. We sort of start off, well, so now when will this not be zero? Well, if B changes with time, that won't be 0. Well, how about if A changes with time? If the area of this thing changes with time, then it's still not 0. How about if theta changes with time? This is not 0. And you're inducing an EMF. Okay, so here are the various situations. You're just changing the strength of B, so you're changing B with respect to time, and you're inducing an EMF. In this case, you're changing the area, and you're inducing an EMF. Now, the easiest thing in practice to do is, rather than changing B or A, changing the angle is the easiest thing to do. Okay, so what you do is, so let's show you that. And here we go. So here is a magnet, okay, and this produces a magnetic field like that. And here is this wire, and you'd rotate the wire. That's the easiest thing to do, and you're changing the angle, okay, while you rotate the wire. So here is the magnetic field, there is the area vector, and as you rotate that wire, that angle changes.
It's doing that thing again that was doing last semester where it's really quickly going back through what already happened.
Yeah, I saw a flicker. Oh. I guess the program will start to the end of the semester. Did it just start doing that?
Yeah.
Okay.
They're just going over.
What's that?
They're just going over everything now.
No, it's a 10-minute time delay. Wonderful. All right, so is this responding in real time?
I think you caught up, yeah.
Okay. All right, so like I said, the EMF induced will come to the negative sign, d by dt of B A cosine theta. And what we are doing is, so here's the A vector, the magnetic field is like that, there is theta, and as I said, theta is the easiest to change in practice. What you do is you rotate this coil, and that'll induce an EMF. And the EMF produced, if this coil is hooked up to the outside world like so, what you get is an AC voltage. All right, so let's make sure we understand this, because in this technology, trillions of dollars have been invested in the world. Well, how do you turn this coil?
So what we were talking about a couple lectures ago, where you use the torque.
Okay, so in a windmill, the wind turns the blades, whose job is to turn that coil. That's at the heart of the windmill. This is a generator. You know? In a coal power plant, what do? You burn coal. From the heat produced, you produce steam. The steam turns this thing. In a dam, the flowing water is what is doing this, turning that thing. Your ultimate goal is to turn that piece of wire. In a nuclear power plant, you split nuclei, energy is released, and from that heat, what do? You boil water. And that steam is turning this thing. Okay? So all the methods of producing electricity currently are doing this. Photovoltaics work differently. Okay? So we are very dependent on this thing. Okay, so that's the AC generator. Again, so if this coil is hooked up to the outside world like so, you get an AC voltage. And if the wire is hooked up like this, you get a DC voltage. Okay, and then of course you can smooth this out. Okay, that's what hold up your block. Mm-hmm. The electric cord for that thing. So all your devices. So this block, that's its job. Okay? It it takes AC voltage and gives you a DC voltage. Okay, well, you know, that's okay. We'll come to that next time. Okay. So this is a DC generator. Okay, this is the AC voltage you have. In this expression, N is the number of turns of the coil, A is the area of the coil, B is the magnetic field strength, and omega is the angular velocity at which it's rotating. Okay? And so the rotational angular velocity is related to the angular frequency of the AC voltage produced. Okay? All right. So this is Faraday's law, and you can see that it's extremely important in our lives. Okay. So again, the induced EMF is minus d by dt of the rate of change of magnetic flux. Okay. All right, so let's see if we understand this. Okay, so here's a circular wire, and here's a bulb attached to it. If you move this magnet in this direction, if you move this magnet, of course, the flux through this thing will change, and the bulb will light up. Okay. How long will the bulb be lit? Exactly. Okay, as long as the magnet is moving, so you can make it oscillate back and forth, and you'll induce a voltage. Okay. What about if you hold the magnet steady and you move this guy, the ring, towards the magnet?
It still stays on.
I'm sorry?
It still stays on.
It will still be lit. Okay. Now this is called motional EMF, but really what is happening is the following. Okay, so if you're sitting in this frame, you're in a moving frame, and this magnetic field that was stationary in your frame this transforms and it produces an electric field which is driving the current. Okay, so that's what's really happening. All right, how about this guy? You have the magnet is steady, is at rest, and you change the area, the bulb will light up. This case, where you're turning the ring like that, it won't light up. Yeah. All right. All right. By the way, so I do have an app here, and so you can see. And if I change the strength of the bar magnet, what I've done, dB by dt is decreased. Okay. And you see, it's not, the EMF induced is lower. Okay. All right. How about this case? So you have a wire carrying a current, which is producing a magnetic field. So again, you stick your thumb out in the direction of the current, and it's producing a magnetic field. So this is producing a magnetic field into the sheet. Out of the paper here, okay? And if this guy moves parallel to the wire, the net flux through this thing is not changing, so it won't induce a current here. If it's moving in any direction other than the parallel to the wire, it'll induce, the flux through this thing is changing, and you'll induce a current. And the direction of the current will be actually, so into the sheet, so the current direction will be like that, okay? And we'll come to that in a second. And if you move perpendicular to this current, the induced current will be the maximum, okay? And the faster you move, the greater the induced current. Okay. All right, so here we go. Here's this magnet, and you move this magnet, you induce a current. And this negative sign is related to the direction of the current. Okay, so that's the Lenz's law. The Lenz's law makes a statement about this negative sign. Okay, the induced current, so here's what Lenz's law says. The polarity of the induced EMF is such that it opposes the change in flux that produces it. So when you move the magnet in this direction, the flux through this ring is increasing, and the induced current is trying to oppose that change. And how does it do that? If the induced current is like that, it's producing a magnetic field in the opposite direction, and it's opposing the increase in this direction. Yep. So when the magnet moves this way, the induced current is that way, and when the magnet moves in the other direction, the induced current is in the opposite direction. Okay. And so this is the basis for speakers or microphones. Speakers and microphones are related. When you have a microphone, you talk into the microphone, what does the microphone do?
Records audio.
So what a microphone does is, so you have a diaphragm here, you talk onto the microphone, which makes this diaphragm oscillate. Okay, so what a microphone does is it converts this mechanical energy into electrical energy. Okay, so behind the microphone is a pickup coil. As this magnet moves, there's a magnet attached to the diaphragm. As this magnet moves, you're inducing a AC current in that coil. So in a microphone, your sound energy got converted to electrical energy. And once you have an electrical signal, you can do all kinds of fun stuff with it. Okay. All right, like I said, this is the basis for a lot of applications in your life. And now we'll talk about a sort of a related phenomenon, motional EMF. Okay. Now what we're going to do is the following. Instead of changing a magnetic field, what we're going to do is we're going to have a steady magnetic field and take a conductor and move the conductor. Okay. So let's say, so in this room, the magnetic field is in that direction, the Earth's magnetic field. We're going to take a metal wire and move it perpendicular to the magnetic field. Okay. Now, if you take this metal wire and move it parallel to the magnetic field, nothing will happen. Okay. For maximum effect, you have to move perpendicular to the magnetic field, and that's what we're going to do. Okay, so let's see what's going to happen. Okay, so the magnetic field is inside into the plane of the paper. We'll take a metal, and this metal has a bunch of free electrons. We'll move in this direction. All right, so when a charge moves in the presence of a magnetic field, it feels a force. So this electron, when you move this electron in this direction, the force on the electron is force on the charge is Q V cross B. V cross B, B is into the plane, V cross B, if you turn this vector, is a force in that direction. That would be the force on a positive charge, but this is an electron, so the force on the electron will be in this direction. Okay, so as long as you're moving this conductor, electrons feel a force in this direction, and a bunch of electrons will collect here, and this end will become positive. So what is happening? As long as you're moving this guy has become a battery. And, well, you can attach this to your oven and warm your pizza or cook your pizza. Yep. So what's going on? It turns out that you have to apply a force to keep this thing moving. So the work you're doing is being converted to electrical energy. Just like that generator. Remember, you needed to do work to turn that coil. Okay, so you move a conductor perpendicular to a magnetic field, you generate a voltage. And the voltage generated is B, the strength of the magnetic field, times the length of the conductor in the magnetic field. and times the velocity. And this velocity is the velocity that's perpendicular to the magnetic field. Okay. So this is called motional EMF, and this can be also thought of, so it turns out that it's one of the Feynman likes to call this the flux rule. The EMF induced is time rate of change of the magnetic flux. So here is the conductor, and if you move this, see the flux through this circuit is changing. And so you can show that the EMF is equal to that. Okay. So as the conductor moves, the flux through this thing is changing. As this thing is moving in this direction, the flux through this loop is increasing. And if the conductor moved in this direction, the flux through that thing would be decreasing. Anyway, the change in flux is equal to the EMF induced across this conductor. All right, as you move this conductor, like I said, you have to apply a force to keep it moving. Why do you have to apply a force? Well, if you move this thing, the induced current is like so, and the induced current, the force on a conductor is I/L cross B. Okay. So if the current is in that direction, that's the L vector. L cross B is into the plane. L cross B is a force in that direction. So because of the induced current, the conductor feels a force, a magnetic force in this direction, and to keep it moving, you have to apply a force. And the rate at which you're doing work is the applied force times the velocity of the conductor. So this is the rate at which you're doing work, and so this is the rate at which you're doing work, and that is equal to the rate at which you're producing electrical energy. Okay. So again, like we keep saying, there's never free lunches in life. Okay. So what is this doing? What is this device doing? What is it?
It's converting energy, it's not creating it.
That's right. Okay. So everything is a transformer. You put in mechanical energy, and that's being converted to electrical energy. Okay. All right. So this thing, we said that so what did we say here? So you take a conductor and you move it perpendicular to a magnetic field. The EMF induced is BLV. B is the magnetic field, L is the length of the conductor in the magnetic field, V is the velocity. Okay? Perpendicular to the magnetic field. And they tested this out. Okay, using the space shuttle. Okay. So here's the space shuttle, and this is a satellite tethered to the space shuttle. And this was 20-kilometer long cable. 20 kilometers is from here to, well, from Ormond Beach to Palm Coast. From here to the beach is about 10 kilometers. Well, okay, so let's say the cable is from the racetrack to the beach. Okay. So they used a cable like that. That's the speed of the shuttle, 8 kilometers per second, roughly. 20 kilometers, and there's the strength of the Earth's magnetic field. So the voltage that should have developed across this cable should have been 8,000 volts, and roughly about 4,000 volts was generated. Again, some of the charge leaks away. Again. But this was tested out. All right, so now we'll say something about this electric field, the nature of the electric field. Okay, so if you have a charged particle, what does it do? What does a charged particle do? What kind of fields does it produce? It produces an electric field, okay? If it were moving, then it would produce an electric field, a magnetic field, okay? So this charged particle produces an electric field like that. And as you go further out, the field strength decreases. Now, the nature of this electric field is the following. It's called a conservative electric field. What that means is if you take the line integral of this electric field around a closed loop, okay, it's always zero. It's a conservative electric field. All right, now we just saw that if you change this magnetic field, so for instance, if you're increasing the strength of the magnetic field, this magnetic field is pointing into the sheet. If you're increasing the strength, it will produce an electric field like this. And you see the line integral of this electric field around a closed loop is not zero. So this electric field was a conservative electric field. This guy is a non-conservative electric field. So the nature of this electric field is different. So, okay. All right, so now we'll talk about applications. Again, this is the flux rule, okay? You induce an EMF as long as you're changing one of these quantities, the magnetic field area or that angle. And like we keep saying, the angle between the area vector and the magnetic field is the easiest to change, okay, operationally. All right, so again, all generators, so you see the generator is a bad name. It should really be a transformer. It's not generating energy, but we call it a generator because it's generating electricity. But all it's doing is converting energy from one form to another. Okay. So in all these generators, at the heart of the generator, you have a magnet. You need a permanent magnet, okay? And you need a coil. And your goal is to turn that coil. Your goal is to change that angle. And there are many ways of doing it, okay? And we name them. Okay, so what are the technologies? How do we change that angle?
We use steam a lot.
Huh?
We use steam a lot.
We use steam a lot. We use windmills. You use ocean wave generators. Okay. Tidal wave generators. They're all doing the same thing. Okay. You can tie your pet dog to and make him turn the coil. All right. Okay, so if this wire is hooked up to the outside like so, using these slip rings, like so, and here are the brushes, then the output voltage across here is an AC voltage. The amplitude of this voltage is given by that expression. N is the number of turns of coils, A is the area of the loop, B is the magnetic field strength, okay? So the stronger the field, greater the amplitude. And omega is the angular frequency, okay? How many radians a second you're turning it at, okay? And the angular frequency of the AC signal is related to the angular frequency of rotation of the coil. Okay. So in the US, we generate a 60 hertz signal. Okay, so the coil is rotating 60 times a second. All right. Well, so in devices, it's not rotating 60 times a second. You massage, it's rotating, well, they convert that signal to 60 hertz afterwards. Okay? So here's a DC generator. If the coil is hooked via the commutator and brushes like this, you get a DC signal like this. Okay, so now here are some fun applications. Okay, so what this is showing you is here's a coil connected to a battery. Okay, when you close the switch, you have a current passing through it, which generates a magnetic field. Before the current was going, the magnetic field was zero. When you close the switch, it generates a magnetic field. And here's just a metal ring. And when the magnetic field through the metal ring changes, it induces a current. And the induced current is such that if this is like a north pole like this, the induced current will be in the opposite direction. And these poles will repel each other, and this will go flying up. Okay. And in fact, you can make, I've seen where this ring can go flying up as tall as this building. It's fun to watch. You guys have seen this device in your bathrooms or garages? What does it do? So this is a safety device that's required by law. Okay. Right, so here is the deal. Okay. What this does is the following. So let's say you're using a hair dryer. Okay. Okay, so it's plugged in and there's current coming in through the hair dryer. It's going through there, the heater element, and then going back. Okay. Whatever current is coming in is the current flowing out. Okay, let's say this thing goes bad while you're using. This wire gets frayed and the wire breaks, and now it touches the housing. The wire touches the housing, and you're holding on to it. So instead of the current going back through there, now is going through you to the ground. It's giving you a shock. And we want to prevent that. Okay? So if the current wire frays accidentally, we don't want the current going through you. So here's how this thing works. Okay? So here's the current coming in. Okay, this current, again, stick your thumb out in the direction of the current, and your fingers tell you this current is producing a magnetic field like that through this coil, and this current is producing a magnetic field outside in the opposite direction. Okay, so as long as the current coming in is equal to the current going out is equal to the current coming in, the magnetic field through this thing is zero. And this sensing coil, it doesn't produce any EMF. Okay, so now let's say this current is coming in, the wire got frayed, and the back current is not equal to this. And now suddenly you have a non-zero magnetic field through this sensing coil, which induces an EMF, and that'll turn off the circuit breaker instantly. It turns off the circuit breaker within a millisecond. Okay, so that's what this thing does. So this is a ground fault interrupter. Okay. So what is its job? If the current going back is not equal to the current coming in, it instantly switches off this device. Okay. Well, within a millisecond. So you do have to survive a millisecond. All right. Okay, so here's an acoustic guitar. When you pluck on the string vibrates and it's making a sound, except that this vibration of the string, the sound is a little too faint. So if you want to hear it, what do you have to do? You have to amplify it. And this box amplifies it. Okay? So that's the amplifier. All right, well, with an acoustic guitar, if you want to entertain a stadium full of 50,000 people, you can't do that. This guy cannot amplify enough for 50,000 people to hear. All right, so what do we do? All right, now we can use an electric guitar. Okay, so here's the string. As the string vibrates, if you magnetize this portion of the string, okay, now you know Faraday's law. You can induce a EMF. All right, so as this string vibrates, you have a sensing coil, and the magnetic field through this sensing coil changes, which will induce a current in this sensing coil. Okay, any vibration, you know how to change it into a current by the use of a magnet. And then you can feed this current to an amplifier. So let's say this vibration in this sensing coil produces a current like that, which is a small amplitude current, but then you can feed this to an electric circuit, an amplifier, and make that into that signal. This you can feed to a speaker and keep 50,000 people entertained. Yeah. So again, what this law allows you to do is, okay, change any vibration into an electrical signal. Okay. So here's another device. So this is a pendulum. So you can take a pendulum, a metal piece, and set it in oscillation. So if it's oscillating here, this thing will oscillate forever. Okay. Now if you take the same pendulum and put it between the magnet, what happens is, as this thing is oscillating, as this thing is going by there, see, this is the North Pole. What it does is it induces a current like that, such that this appears to be a South Pole and the other face will be a North Pole. So the North Pole is attracting the South Pole, and that South Pole is attracting that North Pole, and it'll pull on this thing. So it'll slow it down. So if you get this oscillating in between a magnet, this will stop very fast. It applies brakes. The induced current is such that there's a drag force on it. Now, this is not just of academic interest. You can use this to stop trains. Okay, so this is called electromagnetic braking. All right, so here's a train, and there's the tracks. So if you want to, and this train has these coils which hang close to the track. Okay, I guess it doesn't show you the coils, but anyway, here they are. And when you want to stop the train, all you do is you flip a switch and pass a current through this coil. Okay, and it will induce magnetic fields. It will induce currents in the track such that so if the train were going in this direction, there is North Pole which is pulling back on the train. There is the South Pole pushing back on the train. Okay. And this is the fastest way, surest, fastest, and smoothest way of stopping a train. So you're not dependent on friction. Okay. And this is useful because, train is one of the cheapest way of transporting stuff on land. Yeah. And so if you can pack more and more trains on the track without having to worry about accidents and stuff like that, you could bring down transportation costs. Yep. All right, guys. Oh, here's a metal detector. So here's how metal detectors work at the airports and stuff like that. So you feed an AC signal to this, which is making the flux through this thing change, the receiving coil, okay? And so it's inducing a current in this receiving coil, okay? Now, soon as a metal passes through, if a piece of metal intervenes, this metal, okay, will produce a field in the opposite direction, which reduces the field through the receiving coil, and the induced current in this receiving coil decreases if a metal intervenes. Okay, and that's how you tell if a metal passed. So that's how those things work. All right, so you saw a lot of applications to this flux rule. The induced EMF is equal to rate of change of magnetic flux. Okay? Very important in your lives.